Hello, how you doing? So we're back today, and we're still on Luna with our LunaHopp'r. But one of the things we hadn't answered yet was whether or not this PID tuning that we're doing to hover at a particular altitude, while it works when we jump up from the surface and we come down relatively slowly, uh, how are we going to land from orbit? So last time I said we were going to go. This time we were going to get into orbit, fly around a little bit, and then deorbit. But it turns out the speed of escape velocity for Luna is only 1,000 meters per second. So if you were going more than 1,000 meters a second horizontally in orbit, you would break out of orbit and then end up in orbit about Drew. So what we're going to do is we're just going to crash land. Actually, well, we're going to jump up first, but we're going to jump up to 1 million meters. 1 million meters! And then we're going to come crashing down as fast as possible. We come close to 1,000 meters a second, which is roughly Mach 3. Mach doesn't really matter when you don't have an atmosphere, but relatively speaking. So, at about what would be Mach 3 on Earth, we come crashing down onto Luna, and then we're going to hopefully catch ourselves at 5,000 meters. Oh, I'm on the wrong page. Here we are. So here's our million. There's our waiting for my cursor to come back. So there's our 1,000,000 meter altitude target. Then we're going to come crashing back down, and we're going to try and stop and hover at 5,000. And hopefully our PID algorithm, has enough, or we could, increase these numbers on the PID to make it more reactive. But there's also a possibility we just go too fast for this algorithm to react, because this whole loop, this while loop here, that is recalculating the hover PID values, that only runs so fast, right? So if you're really going fast, you may not be able to even calculate it. So let's go ahead and head on out to the flight line. And this is the same Luna noisy lander that we had before. Of course, all the noise is set to 0, so we're not adding more to the problem than we need to. Oh, and we do have the data, so I wanted to bring up the data on this. So we'll pause briefly. Let me grab the new file. And if you're interested in seeing all the steps behind the scenes here on loading a file into Veusz, look back at our other video. We actually did some on-screen examples. And let's make sure we're reloading the file. All right, and here we go. Here's our data. Obviously, it's still very much in the noise. So we're just going to take off straight up to 1,000,000 meters altitude away from Drew. It's going to be very dramatic, honest. In fact, here's our view. We got the sort of a nice little, what do you call that? Milky Way-ish.
That's beautiful.
And then Drew there in the background. And so we're just actually going to keep firing until we get an apoapsis of 1,000,000 meters, and then we're going to coast the rest of the way. And then we're going to start falling back down. Now, looks like we're missing something on the chart. Let me check this right quick. So on the chart, there we go. I have to reset the view of the range of the data here. And I think that's it. Oh, let's check the x-axis as well. There we go. So I had zoomed in previously and left that zoom parameters in place. So I've got it all reset here. And actually, as you can see, we had that problem earlier, or last time, where we did this sudden jump from 15,000 to 20,000 in our altitude.
Right.
But you can see the red line now is our altitude above sea level, and the blue line is our altitude above ground that we had before. And I don't know if this is a glitch or intentional, but I'm going to use it as a clue that our radar altitude or our LiDAR altitude device doesn't come into effect until we're at 15,000. So what we're going to do is we're going to look at our algorithm and make sure we don't do anything until 15, based on above ground level, until we're at 15,000 15 kilometers or less. Because what that means is we don't have a radar altimeter. We actually don't know how high we are above ground until that point. And we're actually going to be taking quite some time to get up to orbit. So 2.38 hours. I don't think we want to wait for all that. So we're going to go ahead and time warp. Pretty much time warp maximum. And what will happen is once we, you can see our altitude spiked up, and we're already falling back to the moon. It'll slow back down to regular speed once we get close, and then we'll kick on our engines. Here's where we're getting ready to hover at 5,000, right? Except we're at 73,000. And we've got a lot of falling to do. So over here, this third chart is the vertical speed. So you can see we're down near 1,000, negative 1,000. Actually says 892 or 893. And I think we're pretty much going to get up to 1,000 meters a second. And then hopefully things will react and we'll slow down and, you know, actually start to hover. But I don't know. Maybe, maybe not. Our vertical speed just keeps increasing. 929, 930. Oh, let's see. Let's take a look from the onboard camera. I don't know. It's not looking good. We're at 12,000, 11,000, 10,000. Now we get some reaction. Okay, slow down. Slow down. Slow down. Oh. Well, that didn't work. So, as you can imagine, I knew this wouldn't work, and it was part of my dastardly plan. No, actually, obviously, we were going way too fast, and I think we actually saw this before sometime. Let's see. I think we've seen this before. So they think, hey, we're going to send this probe down to this ice planet, right? There goes the probe. There we were just now. Except we're not powering a descent. We're not firing our... And that's pretty much what happened.
Exactly.
Except in the science fiction world, he survives. And he just, you know, hovers on out. Doo-doo-doo-doo. And he flies out. And so this is the kind of thing we're looking for. We want to hover over the ground, be able to investigate, look around, see some poor guy running in the ice. So that was actually kind of the inspiration for this one flight. So we're going to go fix this flight, which is to say, not go so fast. Right?
No.
The primary...
Wrong.
Wrong.
Wrong!
Okay-ish. So we go in, we're going to go edit our program in the box again. And then, as if, you know, it's a baking show, here's our convenient piece of code already waiting for us to slow us down. So what we do is we add to the end of the PID algorithm that does the PID calculations that if our altitude is below 15,000, 15 kilometers, that's where we had determined was the limit, upper limit to our radar altimeter.
Right.
So that's the upper limit.
I said right.
Correct.
Correct.
That's the upper limit, so we can't actually react until then. But if we're below 15,000 and our vertical speed is less than negative 300 meters per second, which negative 343 or so meters per second is Mach 1. So what this amounts to, as this code, is as long as we're below 15,000 meters, and we know how far we are above ground at that point, then if we're going faster than Mach 1, slow down to that's about 80% of Mach 1. And that gives us the ability to actually react in the rest of the algorithm to the changes and slow ourselves down. So just to make this even extra dramatic, we're going to slow ourselves down at 100 meters above the ground. So we're going to come in from outer space, slow down after 15,000, and then land at 100 meters over the surface. Sound like a plan? That's the plan. So just to give you a quick view, I added the altitude and above sea level to the data log. And that was the other line that we're seeing. Alright, so let's head on out. And this should be a nice flight, right?
Good luck.
Good luck. Here goes the flight here. So, these are the times when I wish it was just a little bit faster. That's not a good camera angle.
Oopsie.
Yeah, let's look down while we take off. Why not? Whee!
How much dust is it gonna blow?
Well, that's
it
one of the.
It doesn't blow any dust. That's
it
false.
Doesn't. Yeah, that's one problem here.
Fake info.
We don't have the regolith being blown away from the surface. And we'll actually talk about that in a second, which is one of the issues in all of these landers is how do you go about having a place to land, right? It's one thing to be on a moon. Now, how do you land there, right? Dang it. Two rights in a row. Two rights in a row don't make a wrong. So we'll go ahead and speed this up here. Whee! All the way up. And coming all the way down. Now we're going to target 100 meters above ground level. We're currently going Mach 2. 2.5. And just watch the AGL. I guess I should put up the data for this, shouldn't I? Let's go ahead and bring back up the data here. What's the fun of having the data if you don't show it, right?
You love the data, huh?
Oh, you gotta see the data.
You love it.
I need more data. Dirta? Is it Dirta? Alright, there's the Dirta view. Now you see our flight arc looks very abbreviated because of the warp speed. But here we go. We're still going 890. Can't really see our altitude details because of that big spike.
Right.
So, while we've got a few seconds, I'm going to come back into the tool. And we're going to zoom in on the tail end of the flight data. There we go. So that shows you a little bit more scale, right? It's still 50,000. That's a pretty big gap there.
That is.
Is that a little better? Oh, There we go. Here's our braking burn. So this goal of this burn is just to get below 300.
Look at all the craters.
Yeah, it's not a great place to land. But that's part of why we're hovering at 100 meters above the surface. Okay, we slowed ourselves down decently at about 5,000. Maybe that's why 5,000 wasn't such a good choice. We couldn't even gotten slowed down at that point, right? You also see our altitudes have diverged.
Yeah.
Nice, safe, gentle landing at 100 meters. But not a great place to land, really. There's our landing shadow. That's helpful. Now, this original program was designed with not much in the mindset of... it was originally designed as a self-running test, so it just ran until you ran out of fuel. And that's fine for quick tests. I got a call coming. But I wanted to add a way in so that we could short-circuit these steps and maybe not take so long, and have enough fuel to maybe do more than one hop per trip. So while we're sitting here, we actually got 0 surface speed, which is really good. We got 0 lateral speed. So that's actually a good speed to land at. You don't want to be going too far back and forth. But this doesn't, it looks like we're on a hillside. So let's get down to that direction. I'm going to be done with the data view for the moment. And I want to get down to that end of that pit, to the lower surface level. It looks flatter, just in general. I got 8% fuel to do it with, so let's bring up our direction. So basically just point this in the direction we want to go. Give myself some leaning forward. Now I've got a little lateral speed. I don't want to take too much speed too fast, right? So let's get back to 90. In fact, we'll go ahead and use these. Now we're just cruising along. Looking for a place to land. Let's see. I like this view in this mode. Here we go. Cruising along. We're keeping it right at 100 meters. So you can see we're kind of following the nap of the terrain. We're going to sneak up on people to come out from the bottom of a crater. Instead of landing from the sky where they can target you, you can just land early, follow nap of the Earth, or nap of the Luna, and then pop out from a crater right when they least expect you. Give you a new sense of what we could do with the Space Force, I guess. I don't know. Alright. Looks like we're getting there. I'm running out of fuel, so I need to get rid of this lateral speed before we go to land. So, oh no. Don't do that. Well, I'm not a big fan of these of these controls, but they work pretty well for this kind of thing where you've got your throttle automatically handled for you. So 7, 6, 5, 4. The lateral speed 3, 2, 1. This will pretty much stop us. Alright, so there we are. Get rid of that. And we're still traveling a little bit, but not too bad. If we keep it below 2 or 3, we can land without too much trouble. And of course we got 2% fuel and we gotta wait for the fuel. We've fixed this in the next one. But you can see how we can relatively easy navigate around and look around for a good place to land rather than just taking whatever happens to be right under us. So let's see. Let me just null out a little bit more of the speed there. 1 meter per second. Oh, there we go, 0. I get locked back to vertical. Ooh. And now we're just waiting for our, was it 10%? I thought it was 10%. Maybe when it gets below 10%. That thing. Anyway, it's supposed to have a fuel trigger that says time to land.
Where?
There it goes. There's the trigger.
There it is.
Yeah.
So I'm about 3 seconds off from you.
Are you? Alright. Nice, gentle landing. Isn't that wonderful?
Yay.
Oh, I've had the sound off. Dang it. Hate having the sound off. Alright, so we managed to crash into the planet at super fast speed, slow down with a braking burn, hover at 100, find a place to land, and land. That's the first step of a hopper. Of course, now that you're on the moon, you would refuel from some source on the moon. And you'd want to hop around the moon, do some other things, maybe move fuel. No doubt the poles are going to be where the water is, and if that's where the water is, that's where the electrolysis plant is going to be. Plus, I guess on some part of the poles, there might be a place that's in perpetual light, or pretty close to it. I mean, the reason there's water on the moon is that it happens to be at the deep end of a very deep, in the bottom end of a very deep crater, and that area never gets light from the sun because it's just constantly shadowed. Convenient craters make a convenient bowl shape, right? And so the water at the bottom of the crater never gets hit with the sun, never boils off. So we believe that's where the water is. We land on the pole. We're probably going to have our liquid oxygen, liquid hydrogen plant there. We're going to put that in another rocket, and then we're going to want to move that around the moon, right? So that's our next hopper, where we actually move around the moon. So this was landed. Next, it's hopping. See if I missed anything here in my notes. Yeah, that's good. So now we need to be hopping off. So let's get that going. So let's see. I can go away. So the next problem in this landing that we didn't really discuss because we didn't have a lot of ability to short circuit the program. So the program just came in, it landed, it got to a point where it was hovering, and then it would just stay there until it ran out of fuel. We want a way to short circuit that. So in this next lander, I've put in a little bit of more control, and this is going to be the LunaHopp'r.
Alright.
So the first one was our original Hopp'n, which we did a lot of work on Earth with, Earth drew. First off, and then now we're going to so again, top part's all the logging, and instead of having this being on start and countdown and launch and so on, what we're going to do is put that in a loop, and then I can use one of the activation groups, activation group 10, number 0 on the keypad, to repeat this sequence so that we're not tied to the single trip and then have to restart the whole game, right? So as long as we have fuel, we can make multiple hops. So that's what this little loop here does. And so we basically turned all this into one big function, the hop sequence. And instead of a target AGL of 1,000,000, we're going to 11,000. And what that's for is so that we can actually point ourselves in a given direction, go 11,000 to an altitude of 11,000 and then land at that other location and actually move around the moon. Also, this hop sequence allows me to guide the craft or point the craft in the direction I want to go first. So otherwise, it's pretty much the same. We want to hover at 100. And then one of the things we added in here is this activation group 1 equals 1. That's the landing gear. So what that allows me to do is move from stage to stage by popping out the landing gear briefly and putting it back. And that lets me go from being hovering at 100 to this next one, which will hover at 15. And the reason we want to hover at 15 for a little bit is to create our own landing pad. And interestingly, this is not at all a theoretical thing. Let me find the tab here. Here we go. How will we handle lunar dust without landing pads? Alright. And this is an article from the folks over at Masten, the lander folks that we've been pretty much modeling everything after. And I won't get into all of the details, but essentially what they're doing is you get to a point where you're hovering at some distance above the surface, obviously within the exhaust plume of your engine.
What do you do with that?
How's that?
What do you do with that? The dust plume?
Well, see, what they're doing is they're hovering high enough up that they're not actually making much of a dust plume, but instead, while they're hovering, they're injecting this other material into the exhaust plume of the engine. That material gets laid down as a layer, so it's essentially a hovering 3D printer that's 3D printing its own landing pad. And what this other portion, this is the landing phase, this is the second stage,
Right.
so that as you actually go to land and your jet has a lot more force against the pad that you just laid down, that pad breaks up in large controllable chunks, which is referred to as a blading. So the landing pad burns away as you land. So you create it, and part of it burns away when you land. And I don't know how robust they are, and whether or not you can reuse the same pad over and over again. But I can imagine one of the trips for the Hopper might be jump up in the sky, go fly over here, and then fly a nice grid pattern back and forth, creating a pad beneath it for other larger craft to come in and land on later. So it's one way of forming a form of construction using the kind of craft that we have already ready to go. So based on this idea, we've actually got that 15-meter hover built in. So we're going to navigate to a particular place that I have navigated to before, and it is essentially the second location on Luna, where our launch pad is perhaps the supply place. We load up with some stuff, and we want to take it out to a different base out on another place, another site on Luna. So we'll go fly and do that real quick. And then hopefully, and I haven't tried this yet, always have one or two things that you're doing for the first time. It makes it interesting. So we're going to fly out on a particular course at a particular angle, and that will get us to a particular location, and pretty consistently. And then just through ballistics. But we don't want to land in that location for a number of reasons. And the actual area is off to the side, and so we'll come in, get ourselves hovering, and then from there we'll find a good place to land. So it is actually over that ridge. Over that ridge? Over that ridge. Oh, that ridge. This is the one. This one little spiky ridge here is the point that I'm navigating to. Or close to it, I should say, because the actual heading is 121, which is actually right that away. So we set our heading to 121. That's where we want to go. Now, we've got a fixed amount of thrust oomph in our launch so that we're consistent each time. So this is kind of a half manual flight, if you will. And we're actually going to take a really shallow pitch angle of 15 degrees. And that's going to lead to some hand flying to get to the end, because I don't have all of this coded yet for all of these modes. But let's see. It'll be fun to try. So activation group 10 is our loop, our hover loop, or hopper loop. And once we get going here, we take off and fire right toward them. And now we've fired, we're going to coast for a while. So this is how I'd imagine you'd actually take stuff from spot to spot. Now maybe you don't tilt over oh so immediately so that your exhaust plume isn't firing back at the building, right? You maybe take off straight first and then tilt over. But minus the little glitches in the roll program, this is a consistent way of getting out to our I don't know, a residential spot on Luna. Maybe it's the retirement home. There's been more than one science fiction story where they thought, well, we'll just make caves on the moon and we'll have all the retired people move in because gravity's 1/6 and it's just so much easier to walk around on the moon, right? So what we're actually targeting is this big crater here. Then there's this little guy, looks like a trilobite. Trilobite crater is what I call him. And right in front of that is this crater that we don't want to land in, but that's what we're targeting. And the actual settlement is right over here on this ridge. So the idea being that we don't necessarily want to come in right next to the residential area. Obviously, if our craft has something wrong or something goes sideways, we want to be far away from the living area. So I stopped to write. Took me a while, but I stopped to write. So normally we would just hover 90 degrees vertical, but that was when we were jumping up and down. Now that we've shot ourselves out forward, we need to get rid of all of this extra lateral speed that we have. And then we're at just the right moment, go back to being locked pointing straight up so as to hover. Oh, I gave this one a little bit of extra impulse. Oh, we're gonna overshoot our encampment. We're only gonna have to fly back to it. And they're just beginning to glint into the screen here, the encampment. These are the previous craft with their parachutes out to be somewhat noticeable. Looks like we're shooting beyond them by a good deal, actually. So at this stage, I don't have control of the throttle. It's all under code control. I guess that extra 1,000 meters on the altitude gives me a little bit more distance than I was expecting. Let's see. Here we go. Coming on in. I got my finger on the trigger.
Hi, new person in the room.
We're about to barely survive landing. No, it shouldn't be too bad. I just have to make sure my surface speed gets to the right spot before I go back to vertical. Come on, slow down. Yay, slowing down. There it is. And luckily, I managed to do that and give myself some backwards thrust, right? Let's take a look at our...
Yeah.
Whee!
Yeah.
Flying the nap of the terrain again at 100 meters. Trying to get back to our guys. We're doing 30 meters a second. That's not too bad as a traveling speed. As you can imagine, every time we go over a little bump or go down into a pit, and then we have to react and come back out, and we increase our thrust. You see the thrust just wobbling all over the place, right? Every time we have to do that, we're burning all sorts of extra fuel. So this is not at all an efficient way of landing at a spot, especially if you know exactly where you're going to land. But it is a reasonably decent way of landing near a spot and then hovering with much less force being put out by the engine. So, as you can imagine, when you're coming in, if you do that suicide burn, so if you do a suicide burn on the moon, you're going to kick up a whole lot of mess, right?
Right. Right.
Dang it. So,
Yes.
yes. Correcto mundo.
See.
Si, senor. So, basically what this amounts to is, we're flying along, and we're just burning a whole bunch of extra fuel. But this has its advantages. We're burning extra fuel, but because we're trying to do is hover, and there's fairly low gravity, that's not a very strong plume, right? We're not putting out very much power to stay hovered. The only reason we're putting out these bursts is because we're traveling over different terrain, and our numbers keep changing. I didn't think we were this far away, but I think we're way over that ridge is where the other guys were. So we got 60% fuel, so we're good. We can still cruise along for a while. Give it a nice little cinematic view. Oh, I hate when this happens. When your cameras are looking up at the sky instead of down at the ground. Ooh, that's a little crooked. Alright, so I think they're over this way. The downside to not having a global positioning system, or a Luna positioning system for that matter. I suppose we'll probably get around to doing that on the moon, if it's not already in the works. Let's see how well we handle this sharp terrain. Hopefully we react fast enough to go up and over and not smack into it. Ooh. Looking scary. Don't smack. Nah, he's good.
You think?
Yeah. It's nothing too terribly sharp. Let's see. Hopefully
that one thing.
they're right. Oh, there's a parachute. There's one parachute. Oh. We're coming up over the hill. The encampment never saw us coming. Ah!
Oh, cool. This is all dead parachutes that you've already killed.
Well, these are other landers who didn't have the ability to refuel or to go again. And while this one does have the ability to go again, he doesn't have the fuel. I should really install a refuel mod. Alright, we're going to tilt backwards and kill our horizontal speed, since this is the landing field for this settlement. And I've played with this enough to kind of get the feel for how far back we need to go, but the numbers still help. So we're going to 16, 15 on the surface speed. And a 3. Alright. So I hate the way that thing swings around. But anyway. There we go. We got that. And we still got a little 4 surface speed that direction. We don't want to go over that ridge. No. Go back this way. It's not a good place to land over there. We go. Oh, we got our shadow there. Hey. All right, we're gonna give it. What we're doing is we're just waiting for the surface speed to kick up to 1 or 2. Then we go straight back to vertical. Ah, vertical. So these two buttons, the prograde and retrograde button, disappear when you're going slowly. Right? Or correct, annoyingly. So if you don't have a direction, if you're hovering, standing still, you don't have a direction that you're going. So there's no such thing as prograde. You're hovering. So the buttons disappear and reappear, and then they're in the wrong place when I go to click. There are hotkeys for locking prograde and retrograde, but there does not appear to be a hotkey for locking vertical. Yes. Slow down a lot. Go back over that way.
Well, that looks like a big hole over there.
Yeah. So we don't want to go into that big hole. That's why this is the landing field, actually. Before we had the Mapp'n, when that'll be the next flight we have. 9. I don't want to be going 9. I think I can also do retrograde. Whoop, 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 whoop. Yep, see, this is the problem when you're not using code to control your rocket. Retrograde, vertical. Alright. We finally got ourselves balanced out. We're still going 2, but we're going in the right direction. 2's fine. I can control 2. Ugh. See the way this thing swings until you actually click it, and then it stabilizes? Alright. Just gonna creep up on them. Alright, close enough. Let's back it up just a couple of degrees to knock out this last 2. And then we're ready to land, so let's activate our landing sequence and pad creation burn.
Pad creation burn?
Yeah, we popped out our legs briefly, and that indicated to the software we want to go to 15 meters above ground level, which, considering we're 6 meters, 7 meters tall, means that our exhaust plume is within about 20 feet or so of the surface, or less. So this is where you would sit, and you would very carefully control your lateral speeds, which we're not at the moment. And you would put out the fuel. This is where we're at this stage here.
Or whatever.
Here we are. As we're injecting the particles to print the surface. Or so we hope. And then when we're ready, we can land by indicating we want to land. By clicking on the game to actually have the keyboard clicks count. There we go. And we land, nice and gentle. Along with the rest of them. Hey, don't fall over now. Don't fall over now. Stand upright. Nope. Well, this is why you gotta null out your lateral speed. Yes? What to do, what to do. I don't think we can get him to jump upwards. Well, let's put the legs away. No, no, legs can't get away. No.
Oh, flipped over almost.
I can do a little bit with the legs. Bloop, 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 bloop.
Oh man.
Bloop, 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 bloop.
You're 46 minutes into it and you flipped it on the ground.
Ah, dang it. And he's got fuel left, which means he could take off in theory. In theory. If he could stand up, he could take off. Alright, well, in that case, let's just Ditch the black box. There it is. I don't know what I did wrong, but somehow I attached the black box, the orange black box, to this little disc, and it just pops out of the craft. Instead, it was supposed to separate the capsule from the craft, and somehow it just attached the box to, I don't know. Anyway, I messed up the build. That's why I don't do build challenges. But in any case, here's our parachute. Right into the dirt. It's already buried. It's a buried chute.
A buried chute.
Buried chute. Alright, so
funny.
let's try one more of these, but with a
You gonna leave
little...
that there?
Yeah, you know. No, I'll undo flight and we get rid of them. I left the 4 there so that we could come back to them, but you saw what happened last time when we started having way too many crafts sitting around. Everything came to a screeching
It was
halt.
horrible.
So let's try this again, but with not quite that distance. Let's go some other place, right? Let's go take a look at that flat area. The Sea of Tranquility for Luna, if you will. Which is an area with a lot of relatively flat spots. So, and it is located right over there, see? So this time we're going that direction.
Okay.
So this is where I wanted to get with the craft. I wanted to have enough autopilot to do all of that controlled hover, but still be able to guide it in different directions and look at different parts of the moon. And as a hopper, it would have to. Let's not go quite so sharply, so that we don't have to land so sharply. Being retrograde at like 15 degrees, that's hard to get right. So we'll do it at 45. It's actually 45 degrees would be the best ballistic trajectory for the greatest distance away from where you're at. So, since straight up would send you straight down, and straight out would have you run into stuff. So 45 is the best angle to get the farthest, lob your ballistic projectile the furthest. There we go, we're all lined up. Start our countdown. And so the goal here is hopefully this area we're going into will be nice and flat, and we can land without having to look around and try and find our friends. Oh, dang it. I didn't look at what angle.
Angle?
What angle did I take off at? What's my course? Ah! I don't know what my heading is, so therefore I don't know what my reverse heading is, and therefore I don't know if I can get back. Because that was the idea. We're going to hop out from here, land somewhere, and then hop back. Because, you know, you're going to have like shuttle runs, if you will, moving supplies about the moon, just like you have aircraft now, moving supplies about the Earth. We're going to actually just double speed this guy. I don't want to go actual warp because I'll probably crash if I do that. And then once we flip over into hover mode, we'll want to, let's take a look at our orbit here. Only 22 seconds, okay. So that's not too bad. This time we won't spend a lot of time looking for a place to land. This looks like a lot better places to land. Oh, I was put it in retrograde. And this way, when we attempt to slow down for 100 AGL, we actually get rid of most of our lateral speed.
Oh, yeah, right.
And then if I go back to vertical at the right time, if I do it at the right time, we still have lateral speed going in the same direction we were going. If I do it at the wrong time, we suddenly have too much speed and we end up going back the way we came, as we've seen already. But since we're coming in at a 45, you know, we're going to be closer to vertical when we slow down than we were last time. So it won't be nearly as bad as strong a difference. So these are all various bits I haven't got coded yet because I haven't got to the point where I can experiment. So get that and I'll put it back to vertical right about there. Yeah, that's decent. 9, 8. 7. Alright. So fairly decent. We actually don't want to go too fast or too far because we want to get back the way we came.
Yeah, that looks like a nice plateau.
It's reasonable.
Who knows, right?
It's really hard to tell, and that's what our next craft is designed to handle, is knowing where you should land. So all we have to do now is get rid of this lateral speed, and we will do that oh so gently. So we line up what angle we're at with the angle we're going, and then we back it up just a few degrees because it's only 6. And then 4, 3, 2, and I gotta hit this button before, or right at 1, there we go. Now we go back to vertical, and we got a slow enough speed to land decently, right? Slow enough lateral speed, and it looks flat. Looks flat enough. Legs out, legs zip. The reason I put the legs back up is because if I don't, it'll just immediately go to land. Whereas right now it's going down to print its landing spot, right? Go down, print your landing spot. Unfortunately, it also introduces a little bit more lateral speed, which we want to eliminate, and we can if we're just careful with our angles. Go angles.
Go angles.
Oh, there we go. Close enough. Land, my pretty.
Well, that's cool.
Hey, decent landing. Now, where did we come from? Oh, I must not have turned that off. So we relaunched. So apparently we relaunched because I guess I didn't hit that button twice. Well, at least we got a little 10-second spot. Unfortunately, we're not going back the way we came. So now we're just going up to, I guess, take a look around. I don't know why we would go this high if you were actually going to just come up and hover, but it's not terribly efficient doing the hover. You really want to do the ballistic flight for the majority of your travels, at least, and then the hover flight for just, you know, sneaking up on the bad guys. Coming up over the ridge. So we'll go ahead and skip the hopper here, leave the hopper here, I should say.
Alright.
And, we'll come back down.
Minutes into it, so.
Yeah, we've got one more to go, and it's the most important. That's the Mapp'n.
Alright.
And the Mapp'n is what allows us to know where we should land, right?
I'm interested in that the most.
Yeah, I think so. So we'll go ahead and leave this guy here. Come back after the fact, maybe. I thought it was interesting that it always says, "Oh, you've left a craft in flight, and it's now unpiloted," right? And therefore it might crash. Well, I've never actually just left my hopper hovering, and then just said, "Okay, well, let's see if I come back. Maybe it'll land on its own."
$1.8 million vessel.
It's not much. Yeah,
It's cheap.
It's a cheap little tester.
It's super cheap.
Yeah, if I only burn through 100 of them, that's $100 million. That's not too bad for a spaceflight program. I think I've only burned through about 50 or 60 that I have record of. So let's go ahead and take a look. This is the mapping program, and the mapping program has a couple of differences in the behavior, as you would imagine, but it also presents a couple of interesting challenges. Okay, well, first off, that's not the Mapp'n. Let us load program. Nope. Easier to say yes than it is to say no. Load craft. The LunaMapp'r. Guess that should have 2 P's, but anyway.
Mappa.
The Mapp'n.
Yeah, it should have 2 P's.
So, the Mapp'n has a couple of things different. Now, first off, it doesn't do more than 1 mission at a time. I haven't gotten that all perfected yet, so he's going to do 1 mission. But he's only going to jump up into the sky. Now, in order to map the surface, we have to fly at a known altitude above the planet that stays the same as we go over the undulating terrain. And so we're going to target our altitude on the above sea level measurement, which is, like you saw earlier, 5,000 off from the ground level, plus 1,000 meters. So we're going to go launch 1,000 meters above where we start. Then everything's going to be based off of sea level readings instead of above ground readings, except, of course, when we actually finally land, we'll need it in above ground level, right? And we're going to hover at 5,100. Now, I picked 5,100 because this particular launch site is about 5,000, right, as we saw earlier, and I want it to be 100 meters above that. So we're going to launch up, come back down. I actually have it doing the 1,000 meter above ground instead of 100, so that, again, I can point the craft in a particular direction, send it off that way to do the mapping, and use that initial burst as a launching pad or a launch in the lateral direction, so that I'm not spending a lot of fuel trying to accelerate laterally, any more so than I was needing to travel with anyway. So I get to save some of the lateral speed from the travel and use that instead of having to have extra thruster for that speed. So here we go. Let's see. It's all above sea level. And this actually begs the question, how do you know what sea level is on a planet with A, no seas, and B, no atmosphere? So we can say I'm at a particular altitude based off of the barometric pressure readings of the differences in the density of altitude on Earth's surface. So that gives you a barometric altitude, and that's what most aircraft use.
Right. Okay.
And in order to make sure you didn't run into terrain, because the terrain could be at the same altitude you were at, they created things like radar altimeters that would show you how far above the actual ground you were. And, of course, a barometric pressure reading in an aircraft has the issue of weather, which in a cold front or a hot front or a warm front or a cold front, the barometric pressure changes. That's how it's a barometer, what we read off a barometer to tell whether or not the weather is good or bad, or will likely become good or bad. And because of those pressure changes, you have to synchronize your altimeter in your aircraft to the barometric pressure reading of the local weather. And this is all sort of standard fare that they read off to you from air traffic control, and you can read up from your various piloting applications. And then once you're above, so far high that you're in the Class A airspace of jetliners at 18,000 feet and above, instead of using the actual current weather, because you're actually above the weather, you're in the stratosphere, and so there should be no pressure differential changes, but they just use a standard of 2992 barometric inches of mercury for the barometric pressure, and then all the planes are using the same setting, so everybody knows what altitude they're at, so that if they're heading towards each other, one's at a higher altitude than the other. So you can go straight at each other as long as one's higher than the other. Get that third dimension of separation. So to make sure everybody's on the same page and everybody's altimeter is calibrated correctly, above those heights they just have a fixed number. But on Luna, how are you going to figure that out? And I don't know. I have this guess, and maybe it's a convenient real thing. Maybe it can be done. I don't know. But imagine, if you will, you stop at a very reasonably high level, right? You've got a radar altimeter. It tells you how high you are above the terrain. So you get there, you hover briefly, you get to 0 vertical speed, so you're hovering, which is the definition of hover. Then you cut your engine briefly, or cut power briefly, and you begin to fall. And the amount you begin to fall, or the rate at which you begin to fall, is directly tied to your mass and the mass of Luna. And in theory, we know the mass of Luna. So if we know our mass and we know the mass of Luna, and we know how far or how fast Luna is accelerating us towards the surface, we can work out the gravitational attraction between us. And if we can work out the gravitational attraction between us and the planet at that instant, we can, in theory, figure out how far we are from the center of the mass of Luna. And that would be our baseline. So our above sea level would actually be above center of planet, or above center of Luna. And that would be calculated using the inertial sensors and the like. I don't know if that's actually doable, but at least it could be used as a way of baselining your altitude and saying, the problem with all this is the mathematics of gravitational functions is such that gravity's so weak that everything's way down in the decimals. And so it might be difficult to maybe come back with a formula that's, plus or minus 1,000, plus or minus 2,000. I don't know how bad the error rate is going to be trying to estimate your altitude above a planetary body based off of your gravitational attraction, which is based off of your acceleration in your accelerometer, after you've already used the ground radar to decide that you're hovering. So maybe that's doable. I don't know if it is. But we're just going to pretend that something like that is giving us a baseline for what above sea level is on this sealess, atmosphericless planetary body. So, all that's to say, we're just going to use what they're giving us. And then, of course, when it comes to actually landing, the difference between altitude above sea level and the altitude above ground level, right? Darn it.
Right.
Correct. The difference in those altitudes is your altitude. Well, I subtract them out in this formula to make it 0. So I'm basically I'm using the target altitude based off of above sea level, but then I subtract out everything above ground level, and that gives us 0 ground level, but in sea level readings. So in the case of where we take off, it's 5,000 above sea level, but the ground level is 0. So we'll be traveling out over the terrain, so we won't be anywhere near where we start in the end. So let's see. All right, this is and again we have our pad printing height and so on. So let's head out to the mapping and do some mapping. And to do that, we are going to bring up our data logger again once we get the game up and the log has started here briefly. If anybody has any idea out there how you go about finding your altitude above a planetary body with no atmosphere, and let me know. It'd be interesting to find out. No atmosphere for barometric readings. No global positioning system for global positioning readings, which we already discussed how not so terribly accurate those are. And then, how else could you do it, perhaps? So we've got this pause so that we can decide which direction we want to go. And there looks like some interesting little bumps in the ground. Or do we want to go way off this big cliff? You want to go off here into the seas? Of course, this will be mostly flat. That won't be as interesting. Let's maybe go this direction. Looks like we'll go over a few bumps and stuff. So, first off, let's attach the data. Attach the data, I should say. And then up here the data. And then we got to target the direction we want to go. And we're not going to be too aggressive in our angle so that we don't have to do so much correction. And we'll keep it to 60. So this is going to launch us into the air. Get us some good lateral speed over the surface. and then we'll see how the top gauge here, this top gauge reacts. And what we're actually showing in this one is instead of logging the ground level, let's let that countdown begin. So instead of logging the AGL and the above sea level and the above ground level, I'm logging the, and it's still zoomed in again. Let's unzoom. Unfortunately, this isn't as easy as I'd like it to be. Y-axis. X-axis. Alright. Now we have our data the way we want. So the red line on this top chart is the there we go. The red line on the top chart is our above sea level, whatever that means. All right. I hate when I click on the preview of the view and not the actual view. All right. So again, we want to go retrograde to slow ourselves down, but not too much because we want that lateral speed to actually do the mapping for us. So you can begin to see the above sea level is the red line. The above sea level minus above ground level is the blue line. And there we go. I actually want a decent amount of lateral speed here.
Right.
So you can see here our vertical speed is a nice little check mark here. I don't know what this would be called, but anyway, we accelerate, we nice and gently decelerate, or accelerate in the negative, actually. This is the 0 line. And then we nicely, reasonably land on 100. So you'll note that our AGL is 351, our ASL is 5097, it's supposed to be 5100. So we're a little below our target. This is also ASL, not AGL now. But the main point in all of this is to show how over here we're hovering on the red, but the blue is actually telling us what the terrain is as we go. So let's accelerate out towards some more interesting terrain, since we ended up only going 5 in the lateral. Let's see, we don't want to... So now we're maintaining a above sea level number, not an above ground level. So we're no longer following the terrain like the creepy little probe was. Instead, we're trying to stay at the same altitude while measuring the terrain below us. Hence the mapping idea.
Right.
So,
Right.
let's move fairly quickly forward. Make sure I'm on the lock up button. Get the surface speed of about, say, 20.
It's definitely a hillside.
Yeah. But it's
Doesn't
not...
look like it is.
So, yeah, and so that's the problem with this, is we're looking at a one-dimensional line, right? So if your hillside's like this, and you're looking down on it like this,
yeah.
and you draw a line through the hillside, it looks pretty level, right? Or correct?
Yes.
It doesn't look level. I'll go back to 0 here. Now we got about 33 feet per second. Now, we're going faster, so we're getting over more terrain, but we're actually going to lose detail, right? We send a ping down with our LiDAR to measure our distance, and we measure that distance 20 times a second. So the faster we're going, the more terrain we traverse in between each sample. So we don't get quite as much detail. Alright, so let's get back into the view and zoom in on the data a bit. We can actually see the profile of it. So clearly we don't want to land here, or there's a downhill slope. And we can just watch the downhill slope eventually flatten out. Well, eventually. Let's see. We can cruise at a little 2x speed without having to change our actual lateral speed. And this also messes with the detail. As you saw with our, instead of a nice parabolic arc that would have been natural, it was all compressed in there because we were using warp. But 2x is the limit to what you can do with your engines burning. So we're cruising along. Let's see. This will be an interesting little area here. Looks like where else looks like I might be a good place to land. Let's see. Kind of cheating here. Should really only be looking out the camera views, right? Except it's not looking the right direction. I don't know why that's rotate instead of pan, but anyway. Let's see, this is how we're flying along. Whee! It always looks like we've gone further than, then we get them back in there and we haven't even hit that part of the terrain yet. We seem to zoom out faster than we should. Alright, and then see how this chart stopped updating? That's one of the headaches of, I can redraw the window, I think. Okay, there it's re-updating. And we're just flying by over and over again. Whee! How long is it going to take to get to that terrain? That doesn't seem a lot longer than I expected.
Yeah.
And our data turned out again. Let's go back to the way it was here. Find it easier that if I undo and get back to the full data set, then I can zoom in again. But you can see how, so far, everything's been below us. Let's see. Where's the cinematic view? Oh, that's our camera view, maybe. The other version of the cinematic view. Oh, look at that. We got all sorts of pit below us. Get back to that view. So now we're actually just now reaching this area. It seems like we're going a lot faster than we are. In fact, am I even still 2x? Yeah. Alright, let's take that off. And let's say maybe we want to land... Well, it looks like it's gotten flat beneath us. Look down. Yeah, that's a reasonably flat spot, right?
Yep.
Now we just have to stop traveling so we can actually land on it. Or go back to it. We got 45% fuel left, so we're probably not making it back to wherever we took off. But that's okay. Because the other thing I noticed about this, well, let's just do some other mapping in some other area, actually, first, before we end it here. Let's see. Actually, don't need that detail. I've got the lateral speed on this bottom chart. So you can see the terrain has come back up beneath us. and is actually getting kind of bumpity. So let's really aggressively slow down, since we're losing track. Apparently that would have been a little ledge if we landed there. A little ledge before the bottom of the crater. There we go, 20 on the lateral, down to 15. And so in this scheme, right, I mean, obviously in a real world, you would have a two-dimensional LiDAR, and this wouldn't be just one profile of where exactly you've been above. But let's see, we want to get out of that ditch. Where's a good landing spot? Looks like over that way might be a better landing spot. Let's go over there. So the more we tilt over, right, the more our thrust is not being directed straight down, and so we have to produce more thrust in order to stay at the same altitude than we would normally. And because of that, every attempt to stay at altitude also increases our lateral speed. And so I've been using that to do some basic navigations. Let's see, looks like the hillside's coming up below us. Oof. Here we go. We want the hillside maybe to, we don't want to be completely in that ditch, right? So it looks like this little area right over here is a decent place to land. And, ooh, 35% on fuel. Clearly that's my next graph. I need to know my fuel. Because I kind of like having this view of it, where you don't have the you don't have all the other stuff in the way. Just hovering nice and flat. No, I guess that's the view out the camera of where we were. Suppose it should be looking down, huh? That's all bumpily. I don't want to land in all that bumpily. Yeah, no, let's keep going. Not too far off. We'll come up this ridge line. How fast are we going? Our lateral speed's nearly 40? Oof, does not look fast. But as long as the hillside's coming up in the blue line, we want some nice flat line on this blue. Of course, we went one direction over the crater for this length of time, and then we turned around and went a different direction over the crater the other way. So these lines aren't, you know, a straight line profile of the crater. But we could do that as a mission, right? We jump up, in with the right. We jump up and stay relatively close to the surface, and then just draw like an XY grid. Of course, the way we have LiDAR, the LiDAR that we have now, can map much larger areas from a higher altitude without having to be so slow mapping over it. We're going slow primarily because of the limitations of the data update rate here. So it looks like we're getting close to a smooth spot. We didn't want to land in that crater. And I think we're not over it, yeah. So now we're looking good. It's reasonably looking flatness beneath us. And as long as we're careful in our slowdown, we can land back in this flat area. I should do it here. We can land right back in this back area, or flat area that we just went over. So again, slowing down, aggressively slowing down. Where are we at? Okay. We'll see our lateral speed drop. If I really want it to drop, I can go like this. Oh, looks like the place we were going to land has dropped off. It's curved up there on the top chart.
Oh, see.
Oh, see. We might want to go. Oh no, it's flattened. It's a little bit down, but it's still relatively flat. I gotta back that off a little bit. Alright, let's see where we're at. 3 meters a second. Two, 1, alright. That's probably good. Looks like a decent enough flat space to land here,
Alright.
according to that chart. And down we go. Oh. Just flap out your legs. Whee! And then
Just flap out your legs.
and you'll note it's targeting 4022. So what it did was right when I made this indication that it's time to land, it did a calculation as to, what's the difference between ground level and my level. And then calculate that's minus 15 is where we want to stop. So we should be getting 120. This should be getting to around 15. We got 5, 4, 3. Our lateral's dying or slowing. 2 slowing on its own, so I don't want to manipulate it too much. Doesn't look like it's slowing though. Oh, you know why it doesn't look like it's slowing?
Yeah.
Because we're 15 meters above the ground, and so it looks like we're going very fast. Now, do we want to land or do we want to take a risk? Because we could take a risk and try accelerating and having a nice fast lateral speed over the surface here and see if we don't run into something. Oh wait, we don't want to do that.
Why?
We could do that with the last one because everything was based on above ground level. We can't do it with this one. In fact, we're in dangerous territory right now because if it weren't flat, we actually made our calculation off of wherever we were right before we went to land. And so if this were hilly, the ground would come up to meet us. We were debating on what to do when the ground came up and hit us. So let's go ahead and get ourselves slowed back down. It shouldn't need much to go slow 2 meters a second. And we're also almost out of fuel. Alright, so you see how unstable the
Yeah.
So the cone and the disc are prograde and retrograde. And when you stop moving in a particular direction, or if you're not moving in any direction, then they're undefined. And so if I can get this thing 1 last meter a second to slow down here. I'm not putting out very much thrust at all, 2%, right? So I'm barely putting out enough to have an effect. So there we go. There's our map of our terrain that we went over. Not obviously a straight line, but so there's the landing, the hopping, and the mapping, all done. And we land, and this time we stay upright because it wasn't quite so much lateral. Well, that was pretty much what we had in store. It went long. Probably could have split it up a little bit. But let's celebrate, shall we?
Yay!
So we drop our black box out the side of the aircraft. Thunk.
How elegant.
Yes, well, you got to leave the black box behind so that people know what you did. And then parachute. So now if I ever happen to be flying around this area again, I can find myself. Well, not really, no. I just kill the guys. Or restart them, I should say. Well, that was pretty much it for this one. Thanks for tuning in. Hope you got a little more info out of it. Yeah. A little more ways to play. And be sure to like and subscribe. And if you want to support us and see more of this more often, it would really help if you sign up on our Patreon. $3 a month for the simple tier, $10 a month for the basic tier. We don't have a whole lot of complexity to it just yet. With any of the $10 tiers, you get the sticker and the... Where did I put those? I should really have the props. You think I should have the props, right? So in any case, like us on all that kind of stuff, and we'll be sure to be seeing you next time. Bye.
Bye.
Take it, button. Yay.